The acceleration of an object is uniform if it is always the same value. So acceleration is a measure of how velocity changes with time, and we can calculate acceleration using the gradients of velocity time graphs like these. They show how an object's velocity changes with time. For these two graphs, we have one straight line graph and one curved graph. For the straight line graph, the gradient isn't changing, which means the acceleration isn't changing. So we can say there is a uniform acceleration. For the curved graph, this gradient is changing, which means the acceleration is changing. So there is a non-uniform acceleration. But how do we know the gradient is changing? Well, let's look at how the velocity changes with time. For the straight line graph, we see the velocity increases by the same amount over 3 even time periods. However, for the curve, if we use the same 3 time periods, we can see that there's only a small change in velocity for the first and a very large change for the last. This is because the gradient is increasing. We don't need a graph to tell when an acceleration will be uniform. Objects will have uniform accelerations when the forces on them aren't changing. For example, when there are no forces, like drag, which would change with speed. But what makes uniform acceleration so important? Well, if the acceleration of an object is uniform, then the following equation applies to it. v squared equals u squared plus 2as. Now this looks quite complicated. In fact, it's one of the most complicated equations you'll encounter at GCSE. So let's break it down term by term to better understand it. Beforehand, we've seen equations where v represents a velocity. But here, it specifically represents the final velocity. This is usually measured in meters per second. Then u represents the starting velocity, and this should have the same units as the final velocity, usually meters per second again. What we mean by starting and final velocity depends on the context of a problem. It could be when an acceleration starts and stops, or it could be when we take our first or final measurement. The context of an exam question will usually make this as clear as possible. Then we have a, which is our uniform acceleration, and this is usually given in terms of meters per second squared. It's very important that as the object accelerates from the starting velocity to the final velocity, that the value of a does not change. Otherwise, we can't use this equation. Then finally, we have s, which is the distance travelled, and this is typically measured in meters. This is specifically how far an object will travel in the time it takes to accelerate from u to v. As the velocity is changing in this time, we can't just do velocity multiplied by time to find this distance. You might come across other uniform acceleration equations which use u and v notation like this, but this is the only one of those equations that you'll need at GCSE. You also don't need to know where this equation comes from, but you should be comfortable using it. So let's practice with an example. A mouse running at 1 meter per second spots a piece of cheese 3 meters directly ahead. The mouse accelerates uniformly and reaches the cheese with a speed of 4 meters per second. Calculate the acceleration of the mouse. So this question specifically says the acceleration is uniform, so we can use the equation we've just learnt. Before we start, we should check we have everything we need and what we need to use the equation for. So for step 1, let's write down the key information and the units. We know that the mouse had a starting velocity of 1 meter per second, as this was its velocity when it started accelerating. Then the final velocity was 4 meters per second. The question refers to this as a speed, but from the context, we can assume there was no change in direction, so we can treat this the same as a velocity. We're also told how far away the cheese is when the mouse started accelerating, and that 4 meters per second was the speed it had when it reached it. From this, we can deduce that the distance travelled when it accelerated from 1 meter per second to 4 meters per second was 3 meters. Then finally, we're asked to find the acceleration. So now we know what we're using the equation for. For step 2, let's rearrange the uniform acceleration equation to make acceleration the subject. Unlike most other equations in physics, we can't use a formula triangle here. We need to knuckle down and work through the algebra. So don't worry if you find this step difficult. This is probably the hardest algebra you'll need to do. It's worth taking some time to practice just rearranging this equation in various ways if you're struggling. So let's focus on the current example and make acceleration A the subject. First, let's subtract u squared from both sides of the equation, so we have 2as on its own. This gives us v squared minus u squared equals 2as. We'll flip this around so that a is on the left, giving us 2as equals v squared minus u squared. Now, to get a on its own, we need to move the 2s to the other side. Since we're multiplying this by a, we move it by dividing both sides by it. This leaves us with a equals v squared minus u squared all over 2s. Feel free to watch that again if you're still a bit unsure of what the steps are and why we do them. Then in step 3, substitute the values to calculate the acceleration. So now we have our rearranged equation. All we need to do is substitute the values we listed in step 1. So we had that v was 4 meters per second, then u was 1 meter per second, and finally s was 3 meters. Putting all of this into our calculator gives us an acceleration of 2.5 meters per second squared.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy-to-follow videos, and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!